Yeah, so without further ado, I will introduce our first speaker, which is John Sipple from Google, and he will talk to us about some fault detection and diagnostic work that he and his team have been doing at Google Research around commercial rooftop units. So, John, take it away.
Thank you very much. That should work. Can everyone hear me okay? All right, great. Well, thank you very much for inviting me to talk. This is the first time I've had a chance to address this crowd here, and I'm kind of humbled, first of all, by the experience here. We're far less experienced than you, so we're going to share with you, or I'm going to share with you some of the experiments we've been doing on our rooftop units, on our ACs, using AI to detect leakage. But I'm also looking to learn a lot from you. Anyway, so what we're doing is we're going to apply AI-based methods. Google's an AI-first company, so of course everything we do has to have AI in it. So the first thing is the word AI, but what we want to do is to detect and diagnose refrigerant loss in commercial AC units.
So you need to Alt-Tab.
Oh, Alt-Tab. Alt-Tab. And go into presentation mode. There we go. Now we're good. Okay, so this is probably preaching to the choir here. Global impact, the effective, the global warming potential of refrigerants is 1,000 to 10,000 more times more potent than CO2 is. There's a huge amount, 12% of refrigerant leaks come from ACs, and it's a huge percentage of all non-CO2 greenhouse gas emissions. And over the next 3 years, we're going to be adding more and more ACs as the temperatures increase. So this problem is only going to get worse globally. So taking it a little closer to home, what you're looking at here is our problem child. This is New York 9th Avenue, looking down on it. And I think that kind of crystallizes the problem a bit. So on one hand, we have Local Law 97 in New York that's really clamping down on leakage. But then you see this massive, rather old building with all these condenser fans on it, and it's an enormous leaker. So obviously, this is a problem for Google as well as the rest of the world. We have a huge inventory, over 820 or so buildings in our inventory. Most of them we own, but several we lease. And we have several thousands of ACs that are all at some point leaking. And so looking a little bit more closely to the Google impact, we have on our fleet, we have to track the amount of, legally we have to track the amount of leakage, and that's done via actually technicians going to the devices, inspecting the devices, and determining whether or not, sometimes less accurate, sometimes more accurate, but we estimate 18% of the HVAC equipment has leaked on a year basis. And then 33% of those are the RTUs, and what's interesting is, of the ones that have leaked, given the ones that have leaked, they've lost more than 50%. So our detection rate is very, very low. It really takes for us to really recognize when something is leaking, for us to detect it, we actually have to have a large amount of leakage. So that's something that we want to curtail. We want to reduce that a little bit. So this is kind of the process that we follow here. We have, probably a very standard approach. We have a system failure, leak causes a system failure, then we have an occupant that complains. This is the case where we have 50% leakage. The device is no longer able to provide the cooling, and we have complaints, and then you have a technician that goes up to the roof and then recharges the device and maybe fixes the problem. So it's a very manual process, and we think Google should be a little bit more advanced in that we need to push the envelope a little bit on this. So what we've done is we've said, well, what can we do from these devices? What can we do to instrument our devices to be able to detect these things better? Where would you be able to detect? If you were able to detect a leakage, early leakage, very, very small amount of leakage, where in this entire refrigerant cycle, where would you touch? What kind of measurements would you take? And we kind of focused on the suction header, discharge header, the liquid line, and we put pressure and temperature taps into those things. We actually physically instrumented those. And that is kind of a challenge to scale this thing wide in a large scale. That's the biggest challenge, is inserting these pressure and temperature sensors into the refrigerant line. We do have other things like the outside air temperature, kind of the status, the amount of current that's going to the compressor. We have all those additional features, and we have a fairly rich feature set that we were able to extract, about 50 or so features on our devices. And so what we did is we created this experiment. This is kind of the flow of our experiment. We have a fleet of devices, 12 devices last year, and that fleet is growing this year in different regions. But what we do is we baseline the model. We make sure the devices are at 100%. And then we have a fleet of equivalent devices, same sort of tonnage, same sort of size. And then from 2 of them, we'll remove some refrigerant at a controlled amount. Maybe 10%, maybe 20%. And so we know exactly how much refrigerant is in there. And then what we'll do is we'll say, well, given the baseline training, can we detect it at X amount of leakage? And then we'll evaluate and adjust the model as we go on. And this is ongoing right now. We've done this. This is the 3rd year. I'm showing you results from the 2nd year, last year's results, but this is an ongoing project that's expanding. So all of this kind of started in 2020. We published a paper at ICML that tied together the idea of anomaly detection based on noise contrastive estimation with integrated gradients or explainability. And that turned out to be a really nice match to do not only detecting anomalies, but also providing explanations for anomalies in terms of features and attributions and expected normals. So we started with that. We built an FDD system around it. We'll talk about that a little bit tomorrow. But now we're extending this here for this particular project. Now, where we're going, what we've done in the bigger picture, and I'll just leave this as a teaser for tomorrow's presentation, is we've kind of decided that a nice idea would be to combine the idea of detection, explanation, or explainable AI with interpretation and diagnostic reasoning using large language models. That's kind of the thing that we're doing right now. That's the initiative. We actually have a pilot in place that's running. But we'll spend most of our time today looking at detection explanation for detecting leakage. So here's a view of our buildings that were instrumented, the ACs on these. These are in the Bay Area, so in Sunnyvale. This is our Sunnyvale campus here. And we have several ACs that we instrumented. This is what they look like, very, very, very common ACs. We've put the pressures, you see the pressure and temperature taps on the refrigerant line. And so what we did is we broke it down, and if I go back here, we had several different cohorts, 12 devices with different tonnages, 4 different tonnage levels. Each cohort had 3 devices on it. So what we did is we had a baseline. The thought was if they are the same tonnage, same size, if they have, then we'll gather a baseline from one, and actually all 3 of them, and then when we start the trial, we have one device that maintains the same amount of refrigerant, and then the other 2, we have different levels of refrigerant that we've removed, and then we hope that the algorithm will detect that. So moving forward, this is an example here. So this is starting with our smallest one, a 10 tonnage device, and what I'm showing here is just a timeline of the experiment, and the green line represents the cooling degree days. So this is the Bay Area, not a very heavily loaded place. The Bay Area in the summertime is not a very, very hot place, and you can definitely see that the cooling load varied dramatically over that period. And what you'll see on the top, the different blue and reddish phases here are the different phases of tests. So the blue is where we brought everything to 100%. So you see on the left-hand side, refrigerant charge was 100%, and then the red area we took and brought them down in different levels. So you can see there in the first test we had 90 and 95%. So we brought it down to 90 and 95, took it 5% and not 10% of the leakage, and then determined whether or not we could detect it. Now what was very interesting is as the season went on, we had less and less cooling degree days. Further on to the right here in October, for example, we had 0 cooling degree days. And so the test didn't result in anything. So the most important phase when we collected was when we had a significant cooling degree day. So the very first 2 phases of tests is where we collected most of useful information. We did this with exactly, these are the kind of the setups, the trial setups for this 3 different cohorts. Now we had 40 tons, and then we had 50 to 60 tons. These are trained, all of them were trained devices. And then up to 75-ton devices, and we had different, as I said, the trials were set up in this way. Now, what we also did is we just kind of looked at the data. Let's see, what does the data actually tell us? If we look at these refrigerant superheat temperatures and subcooling temperatures, what does it look like? So if you look at this chart here, we plotted them against each other. So the blue represents 100% charge. So this is the normal device that's sitting in the cohort. And then the orange represent somewhere in the 90s, so a mild leak, and then red represents a greater than 90% leak. And you see that there's a high degree of overlap. Very, very hard to separate these things. That's what we found is it's very hard to separate just by looking at this data. So it's a pretty challenging problem. We found that there were several confounders. So I already showed you the uneven cooling degree days. That the weather was. The Bay Area is not the best place to do an experiment like this. So we're actually going to New York now with much more significant cooling degree days. And we had several data gaps. That was just kind of normal in the data collection. Sometimes that happens. The features from the different cohorts were there's some cohorts had more features just based on the other measurements we were able to get from them. They were not the same. We had varying device loads. That ended up being a major problem. The assumption that 3 devices of the same make and model on three different buildings in the same geographic area isn't necessarily a good way to create a cohort, because some devices have greater load. They have to support a larger area than other devices. Some are much more active than the others. So that was kind of a reasonable first guess. We learned that's maybe not the best way of cohorting. We're still trying to work through that. And then we had a lot of aliasing and undersampling. We were collecting samples at 5-minute intervals. And so that opened the door for a lot of high frequency signals, like the compressor amperage or so, being aliased. And then we had irregular AC duty cycles. People would turn things on, turn things off, and sometimes weekends were busy, sometimes they weren't. So it was a challenge there for us. What we did was we first said, well, let's see how well the human works. How well can a human detect this? Just by looking at superheat temperature and subcooling temperature, and have the HVAC expert put the decision boundaries on these. And we said, okay, that's kind of the baseline that we want to compare to. We want to at least be as good as a human who's actually studied the charts and said these are reasonable boundaries. And then what we did is as our measure, we used the AUC curve, ROC AUC curve. For this audience, probably don't need to explain that too much. And then we applied different ML methods and different anomaly detection methods. So right now we're focused purely on detection. So we looked at the obvious things: isolation force, one-class support vector machine. We looked at a GAN-based approach, MAD-GAN, multivariate anomaly detection for time series data. And then we looked at MADI, which is multivariate anomaly detection with interpretability. And then we looked at the different ones. And here are the AUC curves from the various configurations and the various different algorithms. And you can see, just by looking at the AUC curves, we're not getting 90%, 0.9 or anything like that. We're getting detectability, but kind of on the edge of detectability. And then we looked across the different tonnage levels here from 10 to 75 tons, and we pretty much saw the same story. Some algorithms did a better job than others. We found that the MADI algorithm outperformed the other algorithms significantly. But we also found that in some cases we were able to detect 5% leakage and 10% leakage, but we couldn't detect 80% leakage, which was kind of ironic. We had to dive down into that. That was the mystery behind this last experiment. And I'll get to that. But here are the kind of the ROC scores, and we compared the top. So if we look at the different cohorts, are shown here 1, 2, 3, 4 on the left-hand side. Those are the different devices and the different buildings. And then we wanted to compare the rules-based, the human expert, against MADI, the ML-based expert. And we looked at the different charge levels. So the top here, you see the 70%, 75%, et cetera. Maybe I can point here. Let's see if I can use a pointer. I guess not. Okay. The top there, it says 75 to 95%. And we decided that an AUC score of 60% for each point was enough to be declared detectability. And so you can see here a 95%, so 5% leakage, got pretty good detectability. And then we also had, at 85%, much less detectability, so we had to dive into that. So the other thing that we noted is that the rules-based approach never really performed very well, even though we had an expert to kind of define the decision boundaries and even looking at the data. So the ML solution did a much better job overall, but it still left us with this: why do we have better detectability with a 5% leakage than, say, at the 15% leakage. And we did some explainability analysis. We looked at a lot of the different time frames. And so we wanted to also understand, and when we did detect, correctly detect, when we had a true positive, did we detect it for the right reasons? And so we used the explainability that came out of Matty. It's based on integrated gradients. We looked at different time slices and analyzed that and got a feeling for why certain things were determined to be anomalous. And what you see in the center here with this little pie chart, it shows that the device was labeled as anomalous. So there's red lines at the top, that's the detection. And the blue area here that we've chosen was what we're going to inspect. We're going to analyze it. We found that it was detected as anomalous. And the anomaly detector chose the refrigeration saturation temperature sensor first circuit, and then the second circuit, and the suction pressure sensor. So it looks like the model was able to detect the leakage for the right reasons. We're attributing the fault to the right reasons, and that's useful for us to understand, did the model detect it for the right reason or for some sort of a confounder? So going back to the question about the cooling degree day, or the detectability at 95%, we looked at the cooling degree days, and we found that there's a very strong correlation with the cooling degree days. So what this chart is showing here is where we have the cooling. So now we're looking at cooling degree days versus the machine learning detection. And we saw very strong correlation with the 5% leakage here. On the right-hand column, you see the 5% leakage was also happened to be lined up with the warmest days. So the reason we were able to detect at 5%, which is pretty good detection, was it was also the highest cooling load. So we found that for these ACs, we found this kind of just intuitively, found that ACs are pretty good at concealing leakage and maintaining pressures and temperatures when you have small amounts of leakage. But if you increase the load, as the load increases, it's no longer able to maintain those pressures and temperatures, and that's where you can detect it. So this method seems to work well if it's a high load. It won't detect very well if it's a low load, because the AC is able to kind of compensate internally with those pressures and temperatures. So to conclude, to kind of summarize what our findings here, is in the detectable cases, it outperformed the human expert. We were able to do, the ML methods did better, largely because the humans, they were looking at two features and drawing fixed, constant decision boundaries, whereas the machine learning approach looks at all features and defines an envelope or a manifold around it, and it doesn't have to be a linear, it's a nonlinear manifold. So that makes the decision boundary much tighter. And so that's the explanation we give for why the ML methods outperform the human expert. It generated far fewer false alarms than the heuristics did as well. It still generated false alarms. We still had several false alarms. We're still working on that. It's still very much an imperfect algorithm, imperfect solution, but we think there's promise behind it. We saw that there were a lot of external factors, and the cooling degree days was the biggest thing. So the reason we were able to detect at 95% or at 5% leakage and not at 85% is because the 85 happened to be on a very cool day, on several cool days. We did see that there was a weak but significant correlation between the charge level and the detections, and we did find that we didn't find any relationship with tonnage. We also thought maybe the larger tonnage units would be detecting more than the low tonnage, but we could not find any distinction in terms of detectability between different tonnages. We've found that the explainability had, in many cases, found the right, attributed the anomaly to pressures and temperatures, and sometimes other AC features. So there were no clear features that dominated. One of the reasons this was interesting to us is because the cost of installing a sensor is very high. It's a limiting factor for this particular project, and the fewer sensors we can install, the better. So the thought is maybe we can install something on the liquid line and not on a different place on the refrigeration system, but we weren't able to identify that. The model sometimes used different locations, superheat and liquid and different sensor measurements as its attribution. So we couldn't, there was no clear dominating feature that we could really just focus in on. So if we were to take a look at kind of a qualitative assessment, this is kind of what we think. If you look at the leakage versus kind of the peak load or the outside load in terms of cooling degree days, we look at leakage here. So we want to detect early, you know, when there's a very mild leakage and initial conditions here, so that'd be the right-hand column. We found that small amounts of leakage is detectable when there is a significant load. That's definitely a detectable range. However, it's not detectable when it's a very low load. We just simply couldn't detect it. And you can, obviously you can always detect on a hot day, you can always detect a leak. But as the weather gets milder and there's a lower amount of load, it becomes much more difficult to detect. Nonetheless, what we think that the interesting and fruitful and noteworthy part of this is in fact we're able to detect 5% leakage under the right conditions. So what we're doing next is, this is a continuing thing. We are just kicking off the third phase of this season. And we're going to continue the experimentation in the 12 units that have already been equipped with all the pressures and temperatures. We're going to try to work a little bit at a higher sampling rate and see if we can do a better job, see how much of an effect aliasing had in this particular thing. Unfortunately, I would love to be sampling at sub-second levels. But the infrastructure, the network infrastructure at Google, of all things, can't really handle more than at about a minute interval. So we're going to be sampling at a minute and see if that actually improves things. And one other thought was, could we, if we have mild conditions, can we still detect a small amount of leakage? Considering that we would maybe run an experiment on a weekend and really run the building down to the lowest possible temperature, and then create a load that way. And maybe then we can identify a small amount of leak even when the cooling degree day is low. We're also getting our first operational deployment to New York City, so we're actually expanding not only on regular ACs, but we're also now installing on 3 heat pumps in Hudson 315, so one of our buildings in New York City. And that actually is tied into our real-time monitoring, our real-time FDD. So we're seeing kind of the results come through as we experiment with the devices. And as I said, novel device types, we're bringing in additional rooftop units and heat pumps. So being heat pumps, then we can actually do experimentation year round. And then we're also in the process of, for our new acquisitions, our new buildings, we're seeing if we can just tie in with some of those larger units that already have a lot of the larger units now, like in Charleston building, if you've seen it's an enormous building. Those AC units already come equipped with pressures and temperature sensors integrated in the refrigerant line. So we'd like to bring that in and see how it works on larger and more diverse units. So that's what's going on right now in our continuing research. And with that, I thank you for your attention and would love to have your questions.
Just one sec. So folks online, if you have questions, if you could just either drop them in chat or raise your hand on Zoom, and then we can get to you. And then people in the room, if you want to raise your hands, we have a couple of students who will circulate with mics so you can ask questions.
Great presentation, Jiajin Lin from National Renewable Energy Laboratory. I have not question, just want to understand curiosity myself. Does this units you tested have sorts of receivers or accumulators associated with that? When you say 5% leak, 10% leak, how this refrigerant amount compared with the volume of accumulator that holds refrigerant?
So I don't know about the accumulator, but I can tell you about the procedure that we followed. So we actually had every time when we went through these phases, we actually drew the nitrogen. We had a nitrogen flooding. We drew out all of the refrigerant, and we weighed the refrigerant, and then had the proportion taken out that we wanted, and then put the refrigerant back in. So it was a pretty lengthy procedure. But yeah, I don't know about the accumulator question. Sorry.
The reason it's my own understanding, could be wrong, is if you want to measure something in the system on a system level, your refrigerant the leakage should be reflected on the component level. If it's just a drop of level in accumulator, maybe it's not significant enough to impact on the state point of the operation.
Yeah, I think we've
But
tried
I
that.
could be
I
wrong,
think I'm not too familiar. Our HVAC technicians have looked at the accumulator, looked at the ACs, and we found that those were not particularly good in terms of doing early leak detection.
I just want to follow up on that. Question because I think the sensitivity to charge depends upon some certain system characteristics, like what kind of expansion valve you have. If you did have a receiver, which would be unusual, right? But so did you look at all at what those systems, how they're configured, and whether there are those
we did.
kinds of differences?
I personally didn't, but the team did. We did a pretty good analysis of each one of those devices to see, where could we actually do a physical, detect, look at the flow, but they were not, none of those methods were actually very reliable.
No, I wasn't talking about method. I was just talking about trying to understand if there are differences between the different systems.
Oh.
Because if you have a system with a thermal expansion valve versus one with a fixed, expansion device, right? The sensitivity to charge is very different. If you have a receiver, right? Totally different, right? And so I think that could maybe explain some of the issues with
I believe
detection.
there were thermal expansion valves for all the devices.
Okay, that would make sense.
Yeah.
Okay.
Gregor, do you want to go ahead online?
Sure. I was wondering, your tests involve basically labeling the data to be faulty or not faulty. Was the label qualitative, or was it a continuous? Was it a regression problem where you actually labeled it to the charge level, or was it just faulty and non-faulty conditions?
Great question, and I need to definitely clarify that. So yes, we did label the data. So when we collected the data, and it was at a particular charge, each of the observations labeled with their percentage. However, that was only used for evaluation, for testing. The models were trained unlabeled, completely unlabeled. So it was a completely unsupervised problem. The only reason we used those labels was to evaluate, so we could compute an AUC score. The model itself was not a regressive problem. It was truly an unsupervised anomaly detection problem. One of the things that they wanted, folks wanted to have at Google is to say, well, can we detect and predict the level of leakage? Can we actually predict the level of leakage? And we weren't able to find enough information to do that. We didn't get there was too much noise in the system to actually do that reliably. But yeah, the method we used here is completely unsupervised. None of the labels went into actually training the model. We just observed the model, we baselined the model with unlabeled data.
Perfect. Thank you very much.
Thank you. I was wondering, you mentioned you do sampling at 5 minutes, right?
Yeah.
And you said, okay, you want to go faster, 1 minute, and I'm thinking maybe you should go even faster. We're like, I reason a lot from the physics perspective, and in this case, what I can imagine is that if there is less refrigerant, that the dynamics of a cycle, when there's a step in whatever the compressor comes on, it's like a 30 to 1 minute transient or something.
Yeah.
If you can capture that, I can imagine you see a lot more.
That is exactly the point.
Yeah, and then you need sub-minute sampling.
Yeah.
and perhaps just sample every time a compressor comes on, you have a very steep step, and look at that, and you take a time constant, and that's a metric, you can put a cutoff on it.
Yeah.
Suddenly becomes extremely simple. So I would, starting from how the physics work, look at that much more. Another thing, you mentioned with the 5 minutes, the risk you have now is you have very random samples, that you're sampling at transients. And they're not intercomparable at all. And it's things like that I would be very careful with when just doing a data-based approach.
Yeah, that is in fact a real problem. We definitely notice the aliasing, and we would, the compressor ramping is certainly something that we are aware of, but if you're looking at deploying something to a large scale, sampling at sub-minute becomes kind of not a scalable solution when you're talking about 5,000 ACs.
Sorry, but you're Google, I mean, that's not really an argument.
Yeah, that is, you would think, right? You would think. But unfortunately, with the infrastructure we have right now, with all the devices, I mean, ACs are just one type of device. We have hundreds of thousands of devices, and then trying to keep that data rate up. We ultimately, our BMSs, our low-level data is just third-party data. So the data typically gets stuck at that point.
But you just have to keep the samples at around like once or twice a day, and then it's the same number of samples. So you can vary that.
One of the things we're looking into to address this problem is in increasing the sample rate. I was hoping to get something that's sub-minute, seconds or even sub-second sample rate, and see if we can learn from that. And is there a way that we could use in-painting, or could we use some sort of super resolution techniques? So when we're observing the sample at a lower sample rate, we can in-paint it, use super resolution from a training data that had much higher sample rate. That was something that I'm hoping to get to. I don't know if we're going to be able to get it to it this year, because 1 minute sample rate is still very, very, very slow. But that's a direction that seems very tempting to go down and see if we can use that.
Okay, great questions from the room. Thank you all. I know that there are a couple of more questions, but we need to move on to our next speaker. John will be around though, and I'm sure he'd be happy to chat offline.
Thank you very much.